All right, thank you to those who reached out and asked questions about Mathspace. This video is just going to go over 2 questions that you had from Mathspace. Please continue to ask questions in that Google Doc if you need anything else. All right, so the first question we have is we had this function, this exponential function, y equals negative 2 to the x. And the question is, why is this one growth? So I'm guessing a couple of things. We looked at this and said, well, there's a negative there that might make it decay. And then also, this is a graph of your function over here. Notice when you look at the graph, it's shooting off towards negative infinity. All right, so when you're looking at a graph to determine whether or not it's exponential growth or decay, you're going to look at the right-hand end behavior. Just the right-hand end behavior. So your graph is going to be a growth function if when you look at the right-hand end behavior, it is going towards positive or negative infinity. So I know this one looks like it's going down towards negative infinity. It's like growing towards negative infinity. So that it's not leveling off. The numbers are getting larger. They're just getting larger in the negative direction. Therefore, it's going to be growth. So just look at the right-hand end behavior. If it's going towards positive or negative infinity, it's going to be growth. Decay is going to be when your function is leveling off towards the horizontal asymptote, okay? So we want to look at decay because this started at a very large negative number and it's leveling off, okay? It's decaying. Same thing right here. This one started off as a very large positive number and it's leveling off on the right-hand side towards your horizontal asymptote. So that's what you're going to want to check is the end behavior of your graph. All right, the next question we had was on Mathspace question 22. The majority of the questions were just from portion C, but I did just want to go over the half-life formula to make sure that nobody had any questions on that. So go ahead, take a minute and read that, and then I will move on to the explanation here. Okay, so hopefully you read this, and let's just gather the important information here. The important information, number 1, is your half-life. The half-life is 5,730 years. Okay, that's one important thing. And then the other important thing here is that we originally started out with 301 grams of carbon-14. So those are 2 important pieces of information here. All right, so let's just take a minute and look at our half-life formula. So our half-life formula here is, this is our final amount that we end with. A sub naught is our initial amount, or what we started with. This is always going to be 1/2 because you're taking your initial amount and basically multiplying it by 1/2 each time. And I'm sorry that these got messed up. Okay, now you have your numerator here. So your exponent. So the numerator in your exponent is going to be the time that it is spent decaying. Okay, so this is the portion that's going to change each time. The denominator here is going to be the half-life time that is given to you in your problem. So that's going to be the portion that you fill in. So if you think back to that other question that we had, we have 2 portions here. We have the half-life of 5,730. Okay, so that half-life of 5,730, that's going to be your portion that goes right here. The initial amount is going to be that 301. Okay, so that's what your formula should look like. Here's your initial amount, what we started with. The 0.5 is always going to stay there because you're taking that entire thing and multiplying it by 1/2. This is going to be your half-life time, and this top is your time spent decaying. So question B was, how much carbon-14 would be left in the fossil today if the organism died 1,000 years ago? Okay, so died 1,000 years ago, so that is going to be, right now, that is our N, or our time spent decaying. Okay, so you would just fill that into your formula and use your calculator to get that answer. Because we started out with 301 grams, we're multiplying it by 0.5, and then it's been decaying for 1,000 years, and we know the half-life time is 5,730 years. Half of it will be left after 5,730 years. Okay, so here was the next part that was a little bit tricky. So find out how long ago the organism died if the fossil has 43 grams of carbon-14 remaining. All right, so here's what we know. So what does that 43 represent? So that 43 is going to be representing the final amount that I have. So in place of the final amount, I'm going to put 43. Now the question is asking us to solve for n, or how long has it spent time decaying? Well, you have not learned how to use logs for this yet. So what you're going to do is you are actually going to plug this into Desmos to get your answer. So basically you have two equations here. Your first equation is going to be your left-hand side, or y equals 43. Your second equation is going to be your right-hand side, which is y equals 301 times 0.5 to the n over 5,730. And then in Desmos, what your goal is, you're going to find where these two intersect. So where does this piece, this line, intersect with this line? And that is going to be your value of n, or in this case on Desmos, it'll be your value of x. Okay, so I just took a minute and I graphed these for you. So y equals 43, and then y equals your right-hand side of your equation. Now what you're going to have to do is you're going to have to scroll out quite a bit, and then move your graph over until it hits that intersection point. Okay, so then your x value right here is going to be the answer to your equation. So just use Desmos to answer this until we've learned about logs. If you have any other questions, please let us know.